G'day, I'm James. Today, let's play with long subtraction. In fact, I've got 5 ways to play with long subtraction. 5 different algorithms. They've all been used throughout the centuries, and I want to go through them right now. So let's do an example. Let's do something like 432 take away 158 and do it 5 different ways. Your challenge is to see if you can figure out why each of these methods actually work. Now, I'll give the answers away in this video, but I'll give a pause moment in between so you can actually think about why are these 5 different methods actually working. Okay, method number 1, the exploding dots way. So I'm going to say, okay, most people go right to left, which I think is weird. I'm going to go left to right, just as I was taught in my Western culture to read. To read left to right, I'm going to do it. 4 take away 1 is 3, no worries. 3 take away 5, no worries, it's -2. 2 take away 8 is -6. Bingo, I'm done. The answer is 300, -2t, -6. Absolutely solid, absolutely correct. There's nothing mathematically wrong with that answer, actually. Though society thinks it's very bizarre, so I will actually now fix this up for society's sake. For example, what I'm going to do is maybe I take one of the dots here, make that 1 less, make that 2, and put 10 there instead. So now I can see it's 2, and that makes 8 and -6. Sounding better, 280, -6. Still a bit of weirdness there. So I'll do it again. Take one of these dots, makes that 7, and put 10 there. I'll leave the 2 in front, and that makes 10 and -6 is a 4. The answer must be 274. And it actually is. It is 274. Beautiful. That's the exploding dots way. All right. Way. All right. What's called the standard algorithms now become very standard in most parts of the world. So this is the algorithm you probably taught in schools. 432 take away 158. This one actually does go right to left, which is bizarre in my opinion. Okay, so you look at 2 and 8. 2 take away 8, can't do, you can't do. So what you do, you say, okay, I'll take one of these dots, make it 1 less, and make that 12 instead. And 12 take away 8 I can do. 2 take away 5, bother, I can't do that one. So you take one of these, make it 1 less, make that 12 as well. 12 take away 5 I can do, that's 7. 3 take away 1 is 2. Bingo. So that's very familiar. We got 274 again, look at that. But what's really going on in that one? That's actually kind of cool. This weird stuff up here is a little bit strange. All right. Strange. All right, here's the third method. It's called the equal additions method. I believe this was being used as early as the 1600s or so, and it goes as follows. 432 take away 158. Okay, it too goes right to left. 2 take away 8, can't do it. So what I'm going to do is add 1 to the both parts of this subtraction. I'll add a 1 there and I'll add a 1 there. But the ones mean different things. The one here means to make this as 12, but the one here really means 5 plus 1. It really makes that a 6. Right, now I've got 12 take away 8, and it's 4. Now I've got 3 take away 6, which I can't do. Annoying. So I'm going to do equal additions of 1s. I'll add a 1 there and add a 1 there. Now that 1 means a 13 now, but this one means 1 plus 1, which is 2, so I'll make that a 2. 13 take away 6 I can do, that's 7, and 4 take away 2, I can do that one as well. It's 274. Whoa, that was weird. What was going on there? Okay, here comes method number 4. If you think that's weird, look at this 4th method. It's the complementary method. 432 minus 158. The thing is, no, don't do subtraction, that's too hard. Let's make it addition instead. 432 plus something. Then I'm going to add the complement of 158. Now what do I mean by the complement? I'm going to change each of these digits to be what I need to get to 9. For example, 1, to make that a 9, I'll need to add 8 to it. 5, to make that a 9, I'd need to add a 4 to it. 8, to make that a 9, I'd need to add a 1 to it. That's called the complement of 158. There it is. I'm going to add the complement instead. Great. And I see I get 273. 1273. Beautiful. By the way, that answer is not correct. And the way you correct the answer is, oh, that's a bit weird. Just move that front 1 and add it to the last digit. So get rid of that 1 there. 2, 7, and 3 plus 1 is 4. Oh, whoa, whoa. Welcome to the complementary method. What happened there? Try some more examples. Rewatch this video. Try some more examples and see it will get the correct result every single time. The question is then why? Why? Okay. Why? Okay, that was method number 4, but here comes method number 5, the Austrian algorithm. This wasn't very popular. It was popular in Germanic countries in the 1800s, I believe. And it goes as follows. I'll do the same example. 432 take away 158. You write it in a funny way this time. Now, what you do this time, you ask yourself, okay, I'm going to look at the bottom. I'm going to focus on the bottom. It's an 8. There's a 2 there. What do I need to add to 8 to get to 2? You say, I can't. I mean, the 2 is smaller than 8. I can't add anything to 8 and get to 2. But I could add something to 8 to get close to a 2. I could add 4 to 8, and that at least gives me a 12. It'll give me something that ends in a 2. So it gives me a 12, it gives me an extra 1 here. So I'll add 1 here. Okay. Now ask, what could I add to 6 to get to 3? 3 is too small. You can't add anything to 6 to get to 3. But I can get close. I can get to 13. I could add 7 to 6 and I'll get 13. So I'll add a 7 and 13 means I already got an extra 1 here, 2. Now ask, what could I add to 2 to get to 4? Oh, 2 will do it. The answer must be 274. And you know what? It is. It is. 5 times through we see this 274. Wow, that one is bizarre. What happened there? What was I doing? And why does it work? Okay, does it work? Okay, your turn to pause this video, in fact, rewatch these 5 examples and see if you can make sense of them. And when you're ready, I'll go through them too next. Okay, now it's my turn. Let's go through all 5 methods and make sense of them once and for all. Okay, the first one, the exploding dots way. Here's 432 minus 158. You go left to right in this method. 4 take away 1 is 3. 3 take away 5 is negative 2. 2 take away 8 is negative 6. The answer is 300 negative 2t negative 6. Which is actually a correct, mathematically solid answer. There's nothing wrong with that mathematically. It just sounds very weird. To see what's really going on, let's literally see it. Let's draw a picture. Let's draw a picture of a place value chart. I call this an exploding dots machine, a 10-1 machine. You can call it a place value chart. All good stuff, but I've got a box of the ones, I've got a box of the tens, I've got a box of the hundreds, thousands, 10,000s, and so on. Like we only need the hundreds for this problem. And I'm going to represent the number 432 literally as we say it. We say 400. 400s, there they are. 30, that's really 310. English sort of transmuted those syllables a little bit. 310 is really 3 tens. 30, 3 tens. And 2 dots here, 2 ones. Beautiful. Now, people who know me know that I don't believe in subtraction. To me, subtraction is the addition of the opposite. So here what I'm really doing is adding the opposite of 158. I'm adding the opposite of 100. 1 antidot there. Adding the opposite of 5 tens, 5 antidots there. And adding the opposite of 8 ones, that's 8 antidots here. 7, 8, there we go. Okay, so what's an antidot? So we have a dot, and I'm going to put together an antidot. It's going to be like matter and antimatter in science fiction, or maybe it's actually science. Take some matter, take some antimatter, bring them together, and poof, they just annihilate, they just disappear. Take a dot and an antidot, bring them together, and what do you get? I mean, that, poof, nothing. You get nothing there. That's my picture. You get nothing. That's my actual picture. So you can see right here in this diagram of an exploding dots machine, there's a dot, there's an anti-dot, poof, they annihilate. A dot, anti-dot, poof, 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 3 annihilations. And then here, 2 annihilations, poof, poof. And I see I've got 300s, I've got 2 anti-10s, and I've got 6 anti-1s. It really is 300, negative 2t, negative 6. There it is. That's what it really is. All right, but society doesn't like that answer at all. So what can we do to fix up that answer for society's sake? Well, think about it. This is a 10-1 machine. So we know, for example, that 10 1s make a 10, and 10 10s make 100, and 10 100s make 1,000, and so forth. We could do that in reverse and say, well, one of these dots here, one of these 100s, must have actually been 10 10s. And any dot here must have actually been 10 1s. We can undo that process. So let's actually unexplode this dot here. Let's unexplode and make it 10 1s over here instead. 3, 4, 5, 6, 7, 8, 9, 10. So I took one of the dots away here. I've only got 2 left, but I made an extra 10 dots there. Now I've got enough dots in that box to make annihilations. Dot Todd, poof. Dot anti-dot, poof. There they are. Beautiful, beautiful. And I've got 200 and I've got 8 there, 80, and still got negative 6. 280, negative 6. Still sounds weird, but we can fix it up. Because a dot here really must have come from 10 dots over here. 1 10 is really 10 1s. So let's unexplode this one. It goes away and make 10 dots here. 3, 5, 6, 7, 8, 9, 10. So 1 less dot there, make 10 there. And now I've got plenty of dots here to counter those anti-dots, and I get lots of annihilations. I get 6 annihilations, poof, 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 and that will leave 4 dots behind. And I see the answer is now 274. Beautiful, there it is. Grand, that's what's going on with the exploding dots way. Now, before we move on, I should point something out. I actually kind of liked my original answer, which was there. Let me write it again. 300, negative 2, negative 6. 300, negative 2t, negative 6. Because I can see 274 right now from that. Because what's that 3 really? That 3 is really 300. What's that negative 2 really? It's really negative 20. And what's that negative 6 really? Well, it's negative 6. 300 take away 20 is 280. Take away 6 is 274. So I could have seen the answer right away from first wrote it down on the board. 300, negative 2, negative 6. Quick little mental work, 274. Beautiful. I actually like this method a lot. In fact, that's the method I actually do on paper if I actually have to do long subtraction on paper. All right, but actually, this long subtraction method here of the exploding dots way is the standard algorithm in disguise. What we're doing here, I got a weird answer and people don't like it and then I fixed it up. Well, the standard algorithm says, no, please don't ever write down a weird answer. Fix things up as you go along. Okay, here's how you do it the standard algorithm way. Let me clean the board. Okay, so here's the standard algorithm. 432 take away 158. Great. Let me draw that picture again. Let me draw that place value chart. 1s, 10s, 100s. 400, 32, and please add 1 anti-100, 5 anti-10s, and 8 anti-1s. There we go. And here's the standard algorithm. Has the same issues I was doing the exploding dots way, but this time go right to left, and then you can avoid writing weird things down as you go along. For example, look at this rightmost box. 2 take away 8, can't do it. That's saying there's not enough dots here to counter those anti-dots. We need more dots in this box. Okay, how do we get more dots in this box? Let's unexplode one of these. Unexplode that one, make it 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. There's I took one of the dots away from here and I added an extra 10 dots there. Except in this algorithm, ink is really precious. Don't waste ink by writing that 0. You can actually say, no, just don't do 10 and 2. Make that look like a 12 right away. All right, okay. Grand. But now, my point is I've got enough dots here to counter those anti-dots. Lots of annihilations. Poof, 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 poof. 8 of them, I guess. At least 4 behind. I've now got 4 behind. This box. Don't have enough dots to counter those anti-dots. I need more dots in that box. Where am I going to get them from? Get them from over here. Let's unexplode one of these dots. Unexplode and make 10 here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Bingo. So I took 1 here, 3 behind, and I made 10 there. Again, ink is precious apparently. Don't write 10 and 2, make that look like a 12 right away. Okay, because now 12 dots and 5 anti-dots, I've got enough dots to counter those anti-dots, unexplode, kaboom, 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 poof, 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 poof. That will leave 7 behind. 7 behind, and finally 3 take away 1. Yes, 3 take away, this pair here, dot, anti-dot will annihilate. bingo, and leave 2 behind, 274. So the standard algorithm really is the exploding dots way. If you go right to left, you can avoid writing funny digits as you go along, make society happy. If you go the exploding dots way, left to right, don't worry about what society thinks and fix up the society later on. All is good and grand. All right, 2 methods explained. Method number 3. Here it comes. All right, here's the equal additions method. So here's 432, take out 158. There it is pictorially. Again, if you remember, it goes right to left. You say to yourself, okay, look at the rightmost box. Don't have enough dots here to counter that many anti-dots. That seems overwhelming. So how can I get more dots there? And one way to do that is just put in and load more dots. In fact, I'm going to put in 10 of them. Put in 10 dots here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And to counter putting in 10 there, I'm going to take 10 away from here. I'll add an anti-dot there. That anti-dot there is really going to counter those 10 dots there. Do you see that? That actually doesn't change the actual value of the problem at all. What it looks like on the algorithm is to say, I'll put a 1 there and a 1 there, but really make that 12. Yep, really made that 12, and make this now 6. Seems a bit weird. Oh, it's takeaway 6. It's really 6 anti-dots. Ah, that makes sense. 12 actual dots, there they are, and now 6 anti-dots. Now I have enough annihilations here. Poof, 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 at least 4, oops, 4 behind. 1, 2, 3, 4. A bit messy there, it's a bit too fast. That leaves me 12 take away 8 is 4. Now look at this box. I don't have enough dots to counter those anti-dots. How can I get more dots? Just put them in. In fact, I'll put in 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why 10? Because it's so easy to counter that maneuver by putting an anti-dot there. That's really 1 anti-100. That's really 10 positive 10s. That's really done nothing. But it's given me more dots to play with now. So what I've done there is really added 1 there and a 1 there, but that 1 really does make 13 dots. And this 1 here is really 2 anti-dots. There it is. Beautiful. Enough annihilations now. I do all this and lots of annihilations, and I leave 7 behind. Is that 7? That's 7. All right, great. 7. And finally, 4 and anti-2. Yes, 4 take away 2 is indeed 2 actual dots. There is the equal additions method. I believe this was actually happening in the 1600s, this method. Kind of cool. Okay, now the complementary method. This one's actually very curious. You can actually draw dots and boxes and make sense of it that way, but actually there's a better way to see it, I think, just using basic arithmetic without any pictures. This is really 432, take away 158, sure, but think of this as follows. Think of this as, no. Think of this as add 999, then take away 158, and then take away the 999. Do you see it's really done nothing? It's still 432, take away 158. But if you do this little thing in between, this in between calculation, this is actually a very easy subtraction. There's actually no carrying or borrowing, whatever you call it. 9 take away 1 is 8. 9 take away 5 is 4. 9 take away 8 is 1. That's actually the complementary number. So what you're really doing is 432 plus the complementary number, take away 999. Okay, I'll do that right now. 432 plus the complementary number, 841, is 1273. 1273. All right, but this 999 here, don't think it was 999. Think of it as take away 1,000, or I took away too much, and then add 1. Oh, so take this answer, the number plus the complement, then take away the 1,000, get rid of that, there goes 1,000, and add 1, put 1 there. That was like moving that 1 over yonder. Bingo, there's 274, there's the complementary method. That's insane. Actually, this actually is kind of cool. This works in any base. Let me do it in base 2, because actually I believe computers actually use this method to perform subtraction in base 2. Computers write everything in binary, and I believe this is the algorithm, well, at least once was used very often in computer science. Okay, let's do something like 10010, take away 01100. Great. I've written everything as a 5-digit number. That leading 0 doesn't affect anything here, just kept everything nice and visually balanced by making everything 5 digits. That's fine. All right, so instead of doing subtraction, our job is to actually add the complement. Now in base 10, we're adjusting the digits to get what you need to add up to 9. In base 2, the complement is adjust the digits to add what you need to get to 1. Add to 1. So the complement of this one's going to be, oh, hang on, there's the top lines. The column is what do I need to get to 1? I need a 1. What do I need to get to 1? Nothing. What do I need to get to 1? Nothing. What do I need to get to 1? 1. What do I need to get to 1? 1. Bingo. So let's now add this complement. I see a 2, 0, 0, 2, 1, except I'm in base 2. I know that 2 in a place value, 2 dots in a box actually explode and become 1 dot, 1 place over. 2 here explode, kaboom, make 1 dot, 1 place 0, and 1 place over. And now we have to adjust that, because that's not actually the answer. The adjustment is take the leading digit here, tack it onto that. The answer must be 0, 0, 1, 0, 2. But in base 2, 2 dots explode, kaboom, leave none behind, make 1 dot there. I bet 1, 0, 0, 1, 0, take away 0, 1, 1, 0, 0. In base 2 is 0, 0, 1, 1, 0. Check me on that one. That's kind of cool. Okay, now we come to the Austrian method. All right, the key behind this is take a subtraction problem like 432 minus 158, but actually twist your thinking about what that's really asking. Think of it this as the following question. What do I need to add to 158 to get the answer 432? I mean, it's the same question, but think of it this way. What do I need to add to 158 to get up to 432? That would be the answer to that subtraction problem. All right, so I'm going to literally do that. I'm going to draw a picture of this. I'm actually going to say, here's what I'm starting with. We're starting with 158. 158. 100s, 5, 10s, and 8s. I'm hoping to get to 432. I want 400s, 3 10s, and 2 1s. Starting with that. How can I get that? What can I, okay. So the method says go right to left and say, what could you add to 8 to get 2? I can't get 2 by adding things to 8. But I could get to 12 by adding 4. Let's add 4 right there. If I do that, that gives me 12. And you see why 12 is good? Because then it would actually give me a digit 2. That could be 12 there, still 5 there, 1 there. But then, kaboom, 10 dots explode, leave 2 behind, make 1 there. 162. I've got my 2. Now, I've got a 6 here, but I want a 3. What could I add to 6 to get 3? Oh, too big. 6 is too big. So maybe I should go for 13 instead. I could add 7 now. I could add 7 to this. Beautiful. And that will give me 13 dots there. But that's good. 13 dots is fine. 1, 13, and 2. Because 10 would explode. Kaboom! Leave 3 behind and make an extra dot there. I've got the 2. I've got the 3. Almost there. What could I add to 2 to get 4? I could add 2 to that one. And bingo, if I do that, I will then have 432. Hopefully I'm still on the screen, 432, which is what I wanted. And I got there by adding 2 there, 7 there, and 4 there. I added 2 hundreds, 7 10s, and 4 1s. The answer must be 274. Bingo. There's the Austrian method. This is grand. This is kind of fun. What good stuff.